Hi, hello. Yeah, I think someone raised hand, right? Yeah, go ahead if you have any questions.
Yes, I have a question.
Yeah, sure.
The minimal basis. So the minimal basis was defined as having only one attribute on the right side.
Oh yeah. So how about like we keep the question maybe to the break, right? So then I can answer them.
Okay.
Okay. Cool. Okay. So sorry. Okay. So let's get started. Sorry. Okay. So let's get started. So starting from last lecture, we start to talk about database system, right? If you think about what database was trying to do, right? You as a user, right, can create relations, right? Whenever you create relations, database is going to put that on your hard drive, actually query all the information that you have in your database system, right? You can write a SQL query, and then what's going to happen is the database system going to bring the data all the way from your hard drive to your main memory, and then to you as a user. In the first half of the course, we talk about how to use a database system, right? How to write SQL query, what are their theoretical properties, right? So, and also how to design the database schema. So starting from last lecture, we start to talk about database as a system. So we try to open this magic black box and try to understand whenever you are giving me a query, what is the concrete process the database is doing underneath the cover to bring the data all the way from hard drive to you as a user. So the key fundamental property that we to deal with, right, is this memory hierarchy. And we saw this last time, right? So essentially, whenever you have like your main memory, whenever you have your SSD, whenever you have your hard drive, right? So different type of access have different performance. In terms of hard drive, whenever you are doing sequential access, read and write, so that is where you can get the most performance from your hard drive. And the moment you are doing random access, the smaller your unit is, the smaller your effective bandwidth that you are going to get from your device. And on the other hand, if you look at main memory, so they still have the difference between sequential access and random access, right? But the granularity start to be very different, right? So for example, if you think about on hard drive, the difference between sequential access and random access on 4 kilobyte block is couple orders of magnitude. And in main memory, that's only like 1 orders of magnitude. And on the other hand, you can see the huge performance difference between your memory and also your hard drive, right? So there's probably another 20 to 30 times in terms of the sequential access, right? And even more for random access. And that is something we are going to deal with because all of your data are stored on your hard drive. And then your CPU can only deal with data stored in main memory. Your system are going to be bounded by the data movement from the hard drive to your main memory. And the goal is really, if you give me a query, the system try to decrease the amount of data movement between hard drive and main memory to make answering the query much faster. And that's a game we are going to play with. So in terms of database system, right? So we talk about different layers that we are going to have in the system. At the top of the picture, right, is the input of SQL query, and there's a magic black box in the middle, which returns the result of this query. At the bottom of this picture is your relations stored on your hard drive as a collection of files. And database usually works layer by layer, right? So you have the disk manager, right, whose job is really try to make sure all the other layers above it do not need to directly handle the hard drive, right? And then you have the buffer pool manager, which actually try to give you the illusion that all the data are in main memory, so such that everything above it do not need to deal with both main memory and hard drive. And then we have a whole bunch of access method, For example, you do sequential scan on your relation. Whenever we have an index on the relation, we can do index scan, right? So you have different of those ways to access information in a single relation. And then above that, we are going to implement a whole bunch of operators in relational algebra, right? And then above that, we have the query optimizer, which take us into the SQL query, which is very similar to relational calculus query as a declarative, and then try to compile that into a relational algebra expression. And then it's going to execute it one by one using all the operators that we have implemented. So in the next couple of lectures, we are going to go through the database system layer by layer. So last time we talked about the disk manager, right? So the job of the disk manager is really try to interact with the hard drive. You want to allocate the pages or allocate the records. You want to delete pages, so on and so forth. The goal is every single layer above it will not interact with the disk directly. Instead, they are going to talk to the disk manager whenever they need something. And we talk about different ways that the disk manager is going to organize your relation on your hard drive. So given a relation here, right? So the most common way is to really organize them into a collection of files, right? So, and each file contains a collection of pages, and each page is a fixed size block of information stored on your hard drive. So there are multiple ways to organize files, right? We talk about essentially two different ways. Here you are showing, we are showing one of the most popular way, which is organize file as a heap file, right? So, and then we actually open up like the structure of the page. So again, there are so many different ways you can organize information inside the page. Here we show one of the most popular way, which is by doing that using slotted pages. Essentially, you have a whole bunch of slot like in the page, right? So every single slot corresponding to one tuple stored on this page. Essentially, it points to the start of the page, like the starting point of the tuple, and also the size of the tuple. And we also further kind of open up the structure of the tuple, right? So you can have, for example, at the beginning, you have a bitmap. You have 1 bit per attribute, identifying whether in this tuple that attribute take a null value or not, and then you store all of your fixed long attributes, then you store your variable long fields. So this is actually all about disk manager, right? It's try to organize all the relations on your hard drive as a collection of files. In this lecture, we are going to move one layer up. We are going to talk about the buffer pool manager. So what does buffer pool manager do? Essentially, it tries to maintain an in-memory buffer such that all the other layers, starting from access method, have the illusion that all the data are in memory, not on hard drive. So the interface to the upper layer is as follows. The upper layer can actually ask the buffer pool manager to fetch a page, right? If that page is in the main memory buffer, the buffer pool manager will just return that page. Otherwise, it's going to fetch it from the disk manager, from the hard drive to your main memory and return the call. And it can update the page and so on and so forth. So let's talk about buffer manager first. And then in the second half of this lecture, we are going to talk a little bit about access method. Okay, so what do they do, right? So essentially, you have all your relation organized as a whole bunch of pages on your hard drive, which is the bottom part. And then buffer pool manager essentially try to maintain an in-memory buffer. In this example, you can see there are 2 pages in this in-memory buffer. This is one empty page, another empty page. So what's going to happen is the layer above the buffer manager is going to give it a request saying that, for example, I want the blue page, okay? In this case, we want this page. And then what's going to happen is the buffer manager going to check whether the blue page is already in my buffer or not. If it's in my buffer, it's going to just return it. If it's not in the buffer, is going to actually fetch the blue page from the hard drive to the memory buffer. It's going to take up the space of one slot. And then it's going to tell the upper layer, okay, so here you go. Your blue page is in the fourth slot of this in-memory buffer. You can do whatever you want with it. And then the upper layer could send another request. For example, it will say, okay, so now I need the red page, right? So again, the buffer manager is going to check whether the red page is in the buffer or not. If it's not in the buffer, it's going to fetch it from the hard drive and then tell the upper layer the slot ID of the red page. And then the upper layer will continue to do this. For example, it can say, okay, now give me the yellow page. So here is when the whole thing becomes interesting, because the in-memory buffer will, by definition, smaller than your hard drive, right? Otherwise, you can just copy all the data to memory buffer, you're done, right? So in-memory buffer is much smaller. So at some point, you will have the scenario, buffer is actually full. There's no empty slot in the buffer anymore. But you need to fetch another new page from your hard drive to the in-memory buffer. Here, one key design decision the buffer manager needs to do is to really pick one page to evict from the DRAM back to the hard drive, and then open up an empty slot, and then read this yellow page, and then get back to the upper layer. So as you can see, the buffer manager is really trying to do this very simple thing, right? It gave everything above it an illusion that all the data are already in DRAM. Everything above buffer manager will not deal with I/O. Okay. So on the other hand, one key design decision that the buffer manager really need to do is really try to pick a page to evict when the buffer is full. So this is one example interface of a very simple buffer manager, right? So, and we can go through this one by one, right? So like what method does this buffer manager really provide, right? For example, it can actually return how many buffers do I have and how many pages are kind of already occupied in my buffer, right? And people can like the upper layer can talk to buffer manager to say, okay, I want you to pin a page, which means that I need you to bring one page from hard drive to the buffer and return to me. You can unpin a page, right? Which is which is one way for the upper layer to tell the buffer manager, okay, I do not need this page anymore, right? Feel free to evict it like you need it. And then it can actually create a new page. It can free a page. It can flash page from the buffer to the hard drive. So as you can see, like all these interfaces are kind of pretty natural for a buffer manager. So I think someone raised hand. Yeah, go ahead.
So it's not really a question, but more like,
yeah,
this is very similar to what the operating system does when assigning virtual memory, right?
Yeah, exactly.
So what is stopping us from just saying, okay, we say we load the whole database into memory and then just let the operating system do all the page stuff? Like, why does the DBMS implement its own buffer manager?
Oh, that's a very good question. So essentially, we are going to actually talk about that like later in the lecture. In database, you have actually more information compared with your file system, right? For example, whenever you are having a SQL query, you actually know more about the access pattern, right? So essentially, you can actually implement different ways to evict the pages. And on the other hand, if you are doing kind of the buffer inside operating system, I think most of our operating system will just do LRU, right? So essentially, in database, we do have more information to have a better buffer manager, right? That answer your question?
Yes, thank you.
Yeah, so and later on, we are going to talk about the kind of very interesting example about how these two buffers going to interact with each other, right? And then there's one really emerging research topic, right, in the last couple of years is about how to co-design the database system and the operating system to make sure these two buffers can work together, right? So yeah, so that's actually very interesting. And also like some database, like a company will have an operating system just built for a database, right? And like, and then you can actually start to merge these two, right? Okay, Great. So essentially, when we talk about the buffer manager, right? So there's only one fundamental question we need to understand. That is, how can we design the strategy that to pick which page to evict when my buffer is full? So here we are going to decouple this into two smaller questions. The first one is we kind of want to understand a little bit from a theoretical perspective. That is, assuming I know my access pattern. That is, I know in the future which page you are going to access. Assume I know the future, how to do it, right? So this is actually going to give you kind of the optimal strategy to evict the page, because here you know the future, right? You can actually optimize for it. And second question is, in practice, when we do not know about the future, what can we do? So let's talk about the first question first. And there is actually a very classical algorithm proposed in 1966, actually, to really give you an optimal strategy for buffer eviction when you know the future. And that is actually a very simple strategy. So here's the model. Assuming that I have a stream of access, right? Every single 10 point, I know which page you are going to access, okay? And then assume that I'm here, I'm in the blue page, I'm currently here. And then magically, I know the future. I know in the future which page you are going to access and in which order. And assume in my current buffer, I have the black page and red page in my buffer, and then you are actually requesting the third page, the blue one. So there is an optimal replacement strategy that works as follows. For every single page in the buffer, you actually calculate how far away in the future you are going to access it again. For example, for the black page, right? So you are going to count, okay, 1, 2, 3, 4, 5, 6, 7, right? So essentially, 7 is like after 7 access, you are going to see the black page again. And also for the red thing, it's 1, 2, 3, 4, right? After 4 access, I'm going to see the red page again in my access. And then you try to discard discard the block whose next access is kind of like further away in the future. For example, in this case, you are going to evict the black one, right? So because that is really like in the future, right? And you are going to keep the red one, and then you are going to bring this blue one to replace the black one and serve like the upper layer. So this is a very, very simple strategy proposed in 1966. When you know the future access pattern, this strategy is actually optimal. And if you are interested in why it is optimal, there's a very interesting, very short proof, actually in only 2 pages, that you can see in this link. Okay, so one question that you might have in mind is, okay, so why is this algorithm even useful, right? So in many cases, it is not useful because I don't know about the future, right? But there are cases where you do know about the future, right? So this is actually one paper that we had a couple of years ago when I was at Wisconsin, right? So here is actually very interesting. We want to do essentially give sampling over graphs, right? Which is a kind of like over factor graph, which is a kind of one machine learning model, and we really want to scale it up, right? So the workflow is very simple, right? You have a graph. On one hand, you have a collection of nodes, right? So store as V1, V2, V3, V4, right? Store on hard drive. On the other hand, I have a whole bunch of factors, okay? And also I have F1, F2, so on and so forth, and then I have their connection. So the access pattern is I want to sequentially scan all my V1 to Vn, the left-hand side, and then I want to bring the corresponding factor that connected to them to my main memory. Okay, so on one hand, I have sequential access. On another hand, I have a little bit random access. So, and I want to do that again, and again for maybe 100 iterations, right? So in this example, right, you do know which page I'm going to access in the future because the graph structure is fixed, right? So if you do this application, you can actually apply this optimal algorithm for buffer management, right? But in database, it is often the case that we do not know about the future, right? We don't know what the query the user is going to ask in the future. So in this case, what can we do? So there are multiple ways that you can do this. One popular way, which is actually very similar to what the operating system is doing to manage its own buffer, is something called LRU, right? So least recently used. So I think everyone should be pretty familiar with this, right? It's actually very simple. For every single page in the buffer pool, it keep track the time when it last unpinned, right? Essentially when it's last used. And then you replace the frame, which has the oldest or earliest time, okay? So that is the one that is being least recently used. So it's a very common strategy. It's intuitive and simple, right? And it works well for repeated access to popular pages, which is often the case for many applications. So this is a very simple example about what it's trying to do, right? So here I have these 10 pages. I have 3 pages in my buffer, assuming you cannot request the blue one. And then if you ask for the orange one, right? So I'm also going to bring in because I do have free space in my buffer. And then you are going to ask, I think the black one. Yeah, so I still have free space, right? I'm going to bring it in and serve my CPU. And then assuming if you ask for the blue one again, right? So then you have 1 hit in the buffer because it's already in the buffer. So you just do not read anymore, just serve it. And then if you ask for example, the red one, you need to pick one to evict, right? So in this example, you are going to evict the orange one because that's the least recently used and serve the upper layer. So on and so forth, right? If you have the brown one, right? So I think the least recent use is the black one, you evict it, you bring the brown one, you serve CPU. And if you ask for the blue one again, right? So you are going to have 1 hit in the buffer, you just serve the CPU, right? So this is just a very simple example about how LRU work, right? So as you can see, here we actually try to fetch 7 pages from the hard drive to the CPU, right? So I have 5 miss in the buffer, meaning that I actually in total, I load 5 pages from my disk to my buffer to serve the CPU. I have 2 hits of my buffer, means that there are 2 requests, 2 out of 7 requests that I can serve directly from my buffer without talking to my hard drive, okay? So this is a very simple example about how LRU work. So the question is, can we construct a workload that LRU doesn't perform that well? Yeah, yes, I mean, actually we can, right? Because LRU is actually not optimal. So there's one potential problem related to LRU called screenshot flooding, right? So, and we can see that from this very simple example. Where's my mouse? Yeah, and we can see that from this very simple example. Right, so essentially, I'm trying to read this one by one. I'm trying to read blue, orange, black, right? And this red one, the purple one, so on and so on. I'm doing screenshot scan. Okay, so the first 3 pages are actually easy, right? Because I have 3 pages in my buffer. And then whenever I'm reading the red one, right? So I'm going to evict the blue one and bring in the red one, right? And whenever I'm doing the purple one, I'm going to do this, right? And you can imagine what would happen, right? So, and then one problem related to this is if you are doing those like a screenshot scan, and then you are doing this repeatedly. For example, you do from 0 to 9, and then you do from 0 to 9, 0 to 9, you keep doing this. So you can actually try to like repeat this example again, again, and again. Yeah, you are going to see you will always have cache miss, right? So like essentially every single time we'll have repeated screenshot scan, you will always have like buffer miss. I mean, you are never going to serve any page from the buffer because you are going to always evict the least used kind of buffer page. So But nevertheless, LRU is a very powerful strategy. So how powerful it is, there's actually some theoretical result. So essentially, if you're interested, you can actually read this paper. Essentially, LRU is at most twice as bad as the optimal strategy that we talk about, assuming you know the future. LRU is at most twice as bad as that in terms of buffer miss when LRU is given twice the memory. Right? If you think about this statement, it's actually very powerful, right? It actually means that if you give LRU kind of twice larger the buffer, it will not be too bad compared with the optimal strategy, in which you actually know about the future. Okay, so and that is actually why LRU is a very popular strategy that being used in many systems, right? So for example, in operating system, I believe that is the default, right? But there are other strategies, because in database, we do know more about our queries, right? So we can actually design eviction strategies to actually fill the gap between LRU and the optimal strategy. So another way of doing this is called MRU, which is something called the most recently used strategy. It's actually very similar to LRU, but go the other way around, right? So essentially, for each page in the buffer pool, you keep track of the time when it is last used. And whenever I need to evict, sorry, whenever I need to evict the page from the buffer back to my hard drive, I replace the frame which has the latest like use time, right? So the other way around, compare with kind of LRU. So here's one example. Right, so this is the same access pattern as LRU, right? So the first three access will be very simple, right? Because I have 3 pages in my buffer. I do the blue, I do the orange, and I do the black one. Yeah, and then when I do the blue one, right? So it's I'm very lucky it's already in my buffer, so I can just serve it from my buffer to my CPU, right? And then I think I'm going to read the red one. I hope the purple one. Sorry. Yeah, I'm going to read the purple one, right? So in this case, I'm actually going to evict the blue one because that's the most recently used. I bring in the purple one and serve my CPU, right? So and then which one? I want the brown one, right? So here I'm going to evict actually the purple one because that's most recently used. Bring the brown one through my CPU, right? So on and so forth. So this is kind of very simple, very similar to LRU. So why do we need both, right? So here's actually, let me show you 2 examples where they actually make a difference, right? So you can actually see the animation here. So assuming we have repeated sequential access, okay? I have a page from 0 to 9. I'm going to do 0 to 9 by sequential access, and then I go back to 0, do this again, okay? So, and then we can actually put these 2 side by side and to see how they perform, okay? So on left-hand side is LRU, on the right-hand side is MRU, okay? So I have 10 pages, repeated sequential access. I have 5 pages in my buffer. So the first 5 access will be the same between these 2 because I have space in my buffer, who cares, right? So you start to have difference when you are accessing the 6th page. So for LRU, it's going to evict the blue one. For the MRU, it's going to evict the purple one. Right, and you keep doing this. So as you can see in LRU, it's actually going to evict different pages during the sequential scan, but for MRU, it's going to evict actually a single page. It's always like one kind of buffer slot, right? So that's a difference in the access pattern. And we keep doing this. So this is the end of the first part of sequential scan. And then I repeat, I start from the blue one, right? And here start to have difference. right? Because for MRU, the blue page is always in my buffer, right? For the first 4 access in the second sequential scan, I do not have cache miss in MRU. But on the other hand, I'm always going to pay 1 IO for LRU. And you can actually see the difference when you compare these 2 numbers. This is the number of misses, the number of misses, right, for LRU and MRU. So this is actually one example, one workload in which MRU make more sense compared with LRU, okay? Which is very simple to understand, right? So on the other hand, there are workloads in which using LRU actually make more sense compared with MRU. And this is actually another example. We can put them side by side, right? So here you imagine you have a tree structure, you have a whole bunch of pages organized as a tree, and you try to do what we call index scan. You do 0, 1, 8, and you go back to the root, which is 0, and then you try to access another 2 pages, like 2 and 5, and you go back to 0, there's 0 there, right? 0 is the most popular page because that is the root, right? And that root page, the blue one, is always going to be in the buffer of LRU because you kind of keep getting to it. So it will never be the least recently used, right? As you can see, the blue one is always in the buffer. But on the other hand, because you keep getting back to 0, right? Highly likely, the blue one will be the one that you evict if you are using MRU, right? So that's actually the difference between these 2 strategies. When you have some very, very popular page, MRU has a tendency to evict it. LRU, on the other hand, have the tendency to keep it. So, and you can see from this number of misses, right? So between LRU and number of hits, right? So when you keep doing this, you are going to see LRU has fewer amount of misses compared with MRU, okay? So when you go back home, you can actually open this animation and you can try to follow it step by step, right? So once you do the exercise to actually follow it one pass, you will understand this, okay? So as we can see, right? So there are multiple different strategies, and for different access pattern that you have inside database, different access strategy make more sense, right? And this is only the 2 simple one, right? And there are actually more complex buffer management strategies that you could use. So inside database, we have a whole bunch of data access pattern. We have, for example, sequential scan, right? You start from page 1, you go to page 2, page 3, page 4, right? You have those hierarchical access pattern where you have one page which is the root. For example, here is number 1, and you keep going back to it, right? You keep doing 1, 1, 1, right? There's another access pattern. You could have random access. Right? For example, when you have an index lookup, right, you probably have random access like pattern. You can have those like repeated sequential scan, right? You do 1, 2, 3, 4, 5, then you do 1, 2, 3, 4, 5 again. So in database, for different type of queries, you are going to have different data access patterns. And for different access patterns, different replacement strategy actually works better for different cases. And for many queries, the database actually knows the access pattern for this query, and it can actually tell the buffer manager about that piece of information, and then buffer manager can actually pick which strategy to use. And that's a key difference between the buffer of database and the buffer inside operating system. Because when you are building operating system, you do not have the notion of a query, right? You actually do not have that piece of information that the database actually knows about. And because of that, the database can actually do more optimizations in terms of buffer management. And that was the, to answer the question that we had like 20 minutes ago, that's actually one key motivation that why database people want to build our own buffer manager instead of just using the virtual memory inside the database, okay? So there are actually more advanced buffer manager, right? So if you open up a database, the buffer management, the components is actually way more complex than just MRU and the MRU, right? So just give you one example, right? So this is actually a very old research paper. I don't know, maybe like 20 years ago, like definitely more than that, right? So the observation is inside database, you may have many concurrent queries, right? So for example, you are running a database for the bank, right? So at the same time, there are multiple people withdraw money, right? So you have many of those concurrent queries. Each query is composed of a set of operations, right? So key idea is potentially, right? So I could allocate for each query kind of its own memory space. And then within each memory space, I can adjust the replacement strategy according to the access pattern of that query, right? So essentially, when, for example, you have a scan access pattern, you have index scan, some hash join, right? You can actually allocate them in different spaces in my buffer to make sure they do not pollute each other, right? And within each of the separate space, you can pick the best strategy to use. For example, if I know the first region is for scan, I can do MRU, right? So, and then if I know the second one is for index scan, I can do LRU. If I have some random access pattern, I can just run and replace like my pages without introducing bias, so on and so forth. So there are so many things that we need to decide here. For example, given a query, what is the kind of optimal number of pages I should allocate to it, right? And second, given access pattern, which strategy that I should use. So as you can see, it's kind of highly non-trivial, given our limited information about what query user are going to ask in the future. But nevertheless, you can actually play with it and try to do much better compared with simply using LRU or simply using MRU. Okay. So there's one discussion that always come back to us, that is the difference between the database and the operating system. Because as you can see, inside database, we are building some functionalities that you already have inside your operating system. So whenever we get back to this question, the answer always follow a very similar principle. That is, in database, we know more about what is going on, because whenever I'm doing something, I actually know that this access pattern comes from some SQL queries. And then for different components, for example, disk manager and the buffer manager, right? So I actually have more information to optimize my buffer manager for, right? So essentially, potentially, I could do much better. But a very interesting thing here is that now I have my buffer manager inside database, and also I have my buffer manager in my operating system, right? So there could be two buffers, right? So the question is, whenever you have two buffers, there's interaction between those buffers that could cause a problem, right? So we are not going to go really deep into this, but let me just show you one example here, which is actually very interesting. So assuming that we have a buffer inside database, this one, and then we have the file buffer provided by the operating system. And on the hard drive, I have 3 different pages. So assuming the following case, that is the database say, okay, I want the orange page. In this case, the database buffer manager is going to check the database buffer and see, there's actually a blue page there. So, and I need to evict the blue page. So, and then database is going to say, tell the operating system, okay, write this blue page back to the hard drive. If you just do that, think about what the operating system is going to do, right? It's going to trigger one miss in the file buffer, and the operating system actually, in the default setting, going to bring in the blue page to the file buffer, update it, and write it back. So similarly, right? So assuming you have a much smaller file buffer, if the file buffer is full, and the database will say, okay, give me the orange page, and then decide to evict the blue page. What is it going to do? It's going to try to evict the blue page, right? And then going to trigger one miss in the file buffer. And the operating system need to bring the blue page to the file buffer, but the file buffer is full, right? So you need to evict the red page from the file buffer to the hard drive, bring in the blue page, update it, and write it back. So as you can see, whenever you have these two levels of buffers, you could waste a whole bunch of I/O because these two buffers do not know what each other is trying to do, right? So that is why if you look at modern database research, especially in the last couple of years, there's one very interesting topic about database and operating system co-design, right? How can we pass on information between these two systems such that it works better, right? Such that database can still do optimizations because it knows more about information. And on the other hand, how can we make sure these two buffers plays nicely with each other? So that's a very interesting research work recently about the co-design component of these two parts. So this is about the buffer management. Okay, so I guess let's take a break, a little bit longer break. We are 4 minutes earlier. And then when we get back, we are going to move one layer up, and we are going to talk about, given the buffer manager, given the disk manager, how can we implement different access methods to really facilitate the access of information of your relation? For example, how can we do the index array? How can we do B-tree? How can we do hash table? So on and so forth, given that you have a buffer manager. Okay, so let's take a break. I'll be here, answer whatever question you have. We'll be back in 19 minutes. Yeah. Yeah, go ahead.
So I had a question regarding the minimal basis and the construction of a normal form of it. Because so the question was that we define the minimal basis such that each attribute on the right has.
Yeah, can you remind me which lecture, and let me bring back the slides, and then we can. Yeah.
It's just the definition of a minimal basis. I think it was the first lecture in functional dependencies.
Sorry, let me bring back the slides. Give me a minute. Yeah, here, go ahead. Yeah.
So in the minimal cover, it's specified that A in this X2A functional dependency has to be a single attribute.
Yeah.
However, in all the exercises, when they use minimal function, minimal basis for the construction of the Forel normal form, which needs the minimal basis, it is never decomposed into single attributes. So it always has many attributes on the right, although it only should have one. Thus, the result of the algorithm for the synthesis algorithm changes.
Oh yeah, sorry, yeah. So I mean that's kind of our problem, right? So like essentially, whenever you have, for example, X2A, X2A1, and A2, right? So you can always decompose it, and this is equivalent to you have alpha like X2A1 and X2A2, right? Yeah. So like definitely we do this, and so I think like when we do exercise, we actually assume that. I mean, and this one easier to write, right? And they're actually equivalent. So actually, I think we just go for the first one, right? But semantically, they're equivalent, right?
Yes, but the minimal basis would be the second way, and if we construct the third normal form in the second way, we get two relations instead of one.
Okay, so that's a good question. So essentially, you are saying that okay, so that's a good question actually. So I need to adjust my slides to reflect that. I understand your question now. So essentially, whenever we are doing, for example, the third normal form, right? So we are taking the minimal basis and we do the synthesis algorithm. Should we take this form or should we take the first one, right? So that's our fundamental question, right?
Yes, because according to the definition, we should take the lower one, but in the exercises and also on the other slides, always the upper one used. I assume for simplicity, but the outputs of the synthesis algorithms are different, obviously.
Yeah, so that's a very good question. So I will update my slides and send out announcement in the Moodle to clarify that. Yeah. So when I know your question now. Yeah. So and let me clarify that offline. Okay.
Okay. Thank you.
Thank you. It's nice catch. Yeah, I didn't realize that. Yeah. Okay, so let's get started. Sorry. Yeah, let's get started. So in the first half of the lecture, we talked about the buffer manager, right? So which essentially give all the other layer the illusion that your data is already in memory, not hard drive. So now we start to move one layer up and talk about access method. So what's the goal here, right? So the job of all those access method layer. Yeah, sorry, go ahead.
Yeah, sorry, just before you go to access method, I'm not sure, I just had a quick question regarding the operating system interaction.
Yeah.
So you said when the, so can you go back to the slide where you showed, or I'm not sure if it's a slide, but you said when the buffer management system writes something back, then the operating system might need to bring in the page into the buffer.
Ah, okay, I see.
But I mean,
here, right?
Exactly. But I mean, if it's in the buffer, so assuming the buffer is in DRAM, then the operating system shouldn't be needed. So I don't see like, why would the operating system also need to get the page into DRAM, because it's already in DRAM, right?
Yeah. So, so okay. So by default, right? So your operating system also have the write buffer, right? So essentially, whenever like you say, okay, write this page to the file, right? So sometimes you're going to often it's going to cache it in the write buffer.
Okay. Yeah. Okay. Thank you.
Right.
That makes
sense.
So
of course you can disable that. Right. So, but then the whole thing becomes a little bit more complex, right? I mean, you can have those a direct write. I mean, and essentially you say, okay, just flash this page, right? But then you always have the write buffer in the middle, right? So yeah, so here, maybe it doesn't need so maybe this direction is a little bit confusing. I don't mean you have one IO. So I mean the blue page is always going to be in the file buffer, right? So because by default you have the write buffer and the OS will. The hope from the OS is you can batch all the writes and then you write them once, right? So that could cause problem here.
Okay.
That makes sense?
Yeah, that makes sense.
Yeah.
Thanks.
Cool. Okay. Sorry. Okay, access method. So what is the goal here? So essentially, our goal is really provide different ways that you can access data from a relation. For example, I want to have sequential scan of the relation. I may have an index over my relation, and then I can do lookup on my index. Maybe there's a hash table over my relation. I do lookup in my hash table. I can sort my relation, so on and so forth. Right. So in this layer, we are going to provide abstraction about different ways to access information in the relation. So essentially, the interface we are providing to the upper layer, which is all those relation algebra expression, like operator, is we give them a higher level abstraction to access information in a table without interacting with the buffer, without interacting with the disk manager. So essentially, let's talk about kind of at a high level, right? So what do we have? We have the relation I want to store, which is a whole bunch of files on my hard drive. And then I have my in-memory buffer and I have a buffer manager, right? So now I can only talk to my buffer manager now. I'm at the access method layer. I can ask the buffer manager to bring me a page, and then that's it, right? So I can ask buffer manager to create a new page, so on and so forth. That's all I can do. So essentially, we are trying to implement each of those access methods as a sequence of invocations to the buffer manager to access information in a relation. So the simplest access pattern, the simplest access method is sequential scan, which is very simple. I just sequentially scan all the pages stored in a relation. So assuming that we want to do some lookup query, for example, I will say, okay, I want to find a tuple whose attribute x equals to y. Let's think about this. As one example, if you want to have a query look like select star from students where age equals to 5, right? So you could implement this query using the sequential access method, right? So essentially, you bring in page one by one, You bring the first page of this relation, you scan all tuples and check whether you satisfy the condition or not. If they satisfy the condition, you return, otherwise you do not return, right? So this is just, and you bring page 2, page 3, so on and so forth, right? So this is just kind of one example of the access method implemented using sequential scan, right? So what is the performance of this, right? So here, whenever we talk about performance in the course, we only count the IO, right? We count the data movement. So there are multiple scenarios here. First one is when pages are sequentially allocated, right? So doing this is going to essentially do one sequential scan over all those pages, right? So you pay 1 unit of cost in terms of seek and rotate, right? And then for every transfer time, right? When your pages are kind of randomly allocated, right? And then you want to sequentially scan like all those pages, right? So for every single page, you are going to incur 1 random access. And in this case, you are going to pay D number of pages that you want to access in the relation, right? D units of seek and rotate time, and D units of transfer time, right? So and when you need to update tuples during scan, right? You need to write back the updates, and you will pay 1 more unit of transfer time, right? So this is the kind of very simple access method, right? So I just want to sequentially scan all the pages in my relation. I want to check whether some predicate evaluates true for each tuple or not, right? And then that's it. And you can see there's a very simple cost model associated with that. So the question is actually, can we do better, right? So assuming the only thing we want to do, right, is to support funding the tuples whose attribute x equals to y. That's what we want to do. Can we have other access method of this relation that perform a little bit better than sequential scan, right? So that come to us like that brings us to sorry. So that brings us to index, right? So essentially, one potential thing we can do is to build a data structure F over this relation, right? That given some condition, for example, age equals to 5, that's one condition. This magic data structure can just tell us where is the record ID, and then we can just directly bring that from hard drive to DRAM and serve this query. So here we call F is actually an index, and the hope is evaluating F is much cheaper than a sequential scan of the whole relation. So there are multiple ways you can construct this data structure F. You can have a B tree, you can have a hash table, or you can even learn that as a machine learning model, right? So here we are going to go through the first two, build the index as a B tree and build the index as hash table. So let's talk about B tree today, and we are going to talk about hash table on Friday. So B tree is a very classic data structure, right? So like even in like 1979, you can see there's a survey paper of B tree. So clearly people have been working on this for a while, right, up to 1979. So here, whenever we talk about B tree, we actually mean like B plus tree, okay? So B plus tree is a self-balancing tree data structure whose goal is to keep the data sorted. So whenever you search in a B plus tree, do insertion, you do deletion, right? So essentially, you pay log n is number of tuples, right? So in a relation, you pay log n in terms of IO. It's a generalization of a binary search tree in the sense that every single node in the tree contains more than 2 children, right? Essentially, every single node is a page, okay? So that contains a lot of that can contain a lot of children instead of only 2 in a binary search tree. If you think about why do we want that to happen, is we are optimizing for a system that read and write large blocks of data. Right? If you think about hard drive, whenever I'm reading it, I'm reading a block, I'm reading a page, right? So I do not have a finer granularity than a page. So I need to redesign my binary search tree to be more friendly to this type of IO access pattern. So the structure is actually very simple, right? So you can think about the B+ tree as a M-way search tree, right? So it's perfectly balanced. And to enforce that, essentially every inner node in the tree, other than the root, is at least half full. Okay, so assuming every single inner node can keep, for example, like 20 different children, right? So we need to make sure every inner node must be half full, right? It cannot contain less than 10 children. Okay, so and every inner node with k keys, right, has k+1 non-null children. Okay, so and every single node, inner node or leaf node, is a page. So this is actually one very simple example. Assuming in this relation I have 6 tuples, okay, and assume every single page I can keep essentially 3 keys, right? So in this case, I have my leaf page, right? So like I have my leaf node of the tree. Each one of them contains here essentially, for example, 2 tuples, right? So the first page contains 1 and 3, second page contains 6 and 7, the third page contains 9 and 13, right? And for the inner node, right? So I also contain a key. So I have 5 here, means that if you are searching for age smaller than 5, go to this child. If you are looking for things between 5 and 9, you go to this one. If you are looking for things larger than 9, you go to this one. Okay, so it's a multi-way search tree, very similar to binary tree, but the key difference is that every single node is a page, contains a lot of keys that naturally partition the space. Okay, and to make sure the tree is balanced, we need to make sure you every single inner node is at least half full. Okay, you cannot have a inner node that is empty, for example. Okay, and then like you allow that, your tree will actually not be that balanced. So there are 2 flavors of B+ tree, and they are actually very important. Oh, by the way, so there's another thing that like for the leaf node, you also have a pointer to say this is my first leaf node. You actually have 1 pointer linked to the second leaf node, linked to the third leaf node. Okay, so there are 2 flavors of the B+ tree. The first flavor is called unclustered B+ tree. Okay, so in which the like inside leaf node you contain the key, and then you also store the RID of the corresponding tuple, which is a page ID and slot ID. Okay, so for example, if I'm trying to find a tuple in the relation where age equals to 3, I'm going to first go to the root of the B tree. I'm going to find the right leaf node. I look here, I say, oh, like this tuple has age equals 3. And then from this leaf page, I'm going to have the RID of that tuple. I have a page ID, I have a slot ID, and then I can read it in my head file to fetch that tuple. Okay, so if you have this type of things, it's called unclustered B tree. So another flavor is called a clustered B tree. So in this case, every single like leaf node, so the corresponding T, so you actually also store the actual tuples in the leaf node of the B+ tree. Okay, so for example, here, whenever you have key equals 3, I'm also going to store the whole row in this relation inside the leaf node of the B+ tree. If you do that, it is called a clustered B+ tree. So one thing is that you can only cluster the relation like in one way, right? So that is why you can only have at most 1 clustered B tree per relation, and you cannot have 2 clustered B tree per relation, because I can only store the relation once, right? So you either cluster in this way or the other way, right? So you can have multiple unclustered B tree over the same relation, but you can only have 1 clustered B tree over the same relation. Make sense? Okay, so let's try to understand a little bit about the performance of B+tree. Assuming you want to do a point query on B+tree, for example, you want to find a single key, right? So for example, like you say, okay, I want to find this relation where 8 equals 5. So what is the performance? So assuming your node size in B+tree is m, and assuming your tuple, that your number of tuples equals to n, right? So the depth of the tree, it will be in the order of log mn, right? So that's actually how many layers you are going to have in your B tree. So if you are talking about unclustered B+tree, so what is the number of I/O I need to answer this point query? Essentially, I'm going to traverse the tree, right, which is going to incur like log mn number of IOs, because every single time I need to fetch one tuple, like one page from the hard drive to my buffer, right? And then I go one layer down. And then because it's unclustered, whenever I'm finding the right leaf node, I only get the page ID, right? Then I need to take that page ID and the slot ID, and then I fetch the real tuple, right? So that is why when you have unclustered B+tree, and assuming you only have one tuple that satisfies the condition, right? So the number of IO you are going to have is actually log mn plus 1 number of pages in the worst case, right? So and whenever you have a cluster B+tree, right? So you are going to essentially traverse the tree, you find the right leaf node, and because you are storing the actual tuple in the leaf node, right? So in the worst case, you are going to have log mn number of page reads to answer this query, right? You do not need to fetch the actual tuple anymore, right? So because you already have that in my leaf node. So as you can see, right, for both cases, right? So they have different performance. And then the difference is going to become more clear down the road. But here, as you can see, here's actually you have like the only difference by 1, but it could be huge. Okay, so but nevertheless, both of them are kind of faster than sequential scan, right? At least in the worst case. So you can actually do more using B+tree. For example, you can do range query. You can say, oh, okay, give me all the tuples whose age is in this range. For example, age is between 5 and 10, right? So then what can you do? What is the performance model? In this case, again, assume the node size of the B+tree equals m, the number of tuples equals n, right? So again, the depth of the tree is log mn, right? So assuming you have unclustered B+tree, what is the performance model? Essentially, what do I need to do? The thing to do, yeah, sorry, go ahead.
Yeah,
go ahead.
So the depth of the tree, is it really log mn, or why is it not log mn plus 1? Because don't we have to go through the inner node as well?
Oh yeah, sorry. Here I just like ignore that constant. Yeah, so this big O this. Yeah.
Okay, so in the last slide we also, so if you go back to the slide before, so for the unclustered tree and the clustered tree, would it then be log mn plus 2 and log mn plus 1? For access and IO, because we need
actually depends on how you do the rounding of this, right? So so like you can write that down really precisely, but here when I write this down, I have big O in mind. Yeah, so I actually didn't think too much about the constant. Yeah.
Okay, well, that's fine.
Yeah. But the key point is when you do unclustered B tree, you have at least one more access compared with clustered B tree because I need to fetch the actual tuple, right? So and everything else will be the same, right?
Okay.
But the another small thing is they are going to have different M because essentially the leaf node of clustered B tree can only hold a fewer amount of keys because I need to store the actual tuple, right? So that's another caveat. Yeah.
Okay, thanks.
Yeah, so I will update slides to put big O here. Yeah. Okay, so here, right? So when you have an unclustered B+tree, right? So what is the performance model, right? So essentially, you have 3 different terms, right? So you have the first term, log mn, right? Like really try to read 1 page per level to find the right leaf node. And then what you are going to do is going to kind of sequentially essentially scan all the leaf node, right, to find all the keys that satisfy your search predicate, right? So here you actually want to like sequential scan all the pages, like all the leaf node, right? So that contains keys between 5 and 10, right? So how many pages do you need to have, right? So essentially you need to pay the number of IO equals the number of tuples, right? So that you end up having, right, over the page size, right? So this is the number of leaf node you need to scan, right? And then for each of those tuples in the result, right? So because it's unclustered B-plus tree, I need to fetch the corresponding tuple in the underlying relation, right? So because it's unclustered, in the worst case, I could have a whole bunch of random access, right? So it is entirely possible that all the tuple I want is stored in different pages in my heap file. So in this case, in the worst case, for every single tuple, I actually need to fetch one page in my heap file to get the actual tuple, right? So, so in this case, you have, in the worst case, you have number of tuple in the result here, right? So whenever you have a cluster B-plus tree, right? So it's get actually a little bit faster, right? So essentially you still pay one cost here to really traverse the tree, go to the right leaf. And then because I already have the actual tuple in the leaf node, right? So all I need to do is sequential scan all the leaf node and return the tuples, right? I do not need to fetch a tuple anymore because tuple is already in my leaf node, right? So here, the other part is you have number of tuples in the result over the kind of tuple per page, right? So here, one thing that you need to take into consideration is if you compare the tuple per page for a cluster B-plus tree and tuple per page for unclustered B-plus tree, clearly tuple per page in the cluster case is going to be smaller compared with tuple per page like in the unclustered case, right? So it's simply because in the cluster B-plus tree, you need to store the actual tuple, so every single leaf node can only contain fewer amount of those. Okay. So you can actually do insertion in B-plus tree, right? So for example, you can actually insert a tuple into B-plus tree. So the algorithm is as follows. You first find the right leaf node L, right, by just traversing the tree, right? And then you just put data in L. So here, two things could happen. The first thing is if L has enough amount of space, then you are done. You just insert it, you are done. Okay. So, but however, when L is full, right, it cannot like add another tuple in it anymore. You split L and you insert a new key to the parent of L. Okay, so this is actually like very natural. So I think in the textbook you have a more precise definition of this algorithm, but the intuition is actually very, very simple. So let's look at one example together, and then we can understand algorithm. So this actually is something a really good virtualization platform that other people build. Right? It's very easy for you to understand algorithm if you just go through this. So assuming we are talking about the B-plus tree with a max degree equal to 3, okay, essentially every single inner node can have at most 3 children. So assuming I have at the beginning I have an empty B-plus tree, and then first maybe insert a key, for example 31, right? So I have one node, right? So then I have 41. So what would happen, right? In this case, I'm going to find the right leaf node, right? So I have one node here. I put in 41 here. I'll be happy. I mean, I have enough amount of space to hold it. Okay. So since it becomes interesting, we'll insert another thing. For example, if I insert, for example, 37, so I'm going to find the right page. Here's this one, insert 37, and then I'm going to out of space, right? So I don't have enough of slot to hold it. So in this case, I'm going to split this node into 2 different nodes, and I create a new node as a parent. Okay, so I'm going to have something that looks like this. Okay, so here, as you can see, on the leaf node, right? So I have 31, 37, 41, the thing that I have inserted, right? So I split them into 2 different nodes, and then I insert the essentially like one additional key to the parent. Okay, 37. So what if we do another one? For example, insert 100. What should we do? We will find the right leaf node for 100. In this case, it's going to be the one on the right-hand side. I want to insert 100 into this page. Again, I'm going to split it into 2 different pages, right? And then I'm going to insert the key, 1 additional key to the parents. So that's is something going to happen. Find this, split it, insert another key. Okay, so it's as simple as this. So similarly, we can insert another one. If you do 9, what will happen? You'll find the right leaf node. Here you are going to insert 9 here. You still have space, so it doesn't need to split the node. Okay. So if you do 91, right? So similarly, right? So you are going to find the right leaf node. Here's kind of this node. You insert it. Now you're going to split it. So essentially, you have 2 leaf nodes. You insert 1 more. But in this case, the parent is also going to be full. So you are going to split the parent. Okay, that's what's going to happen. Okay, so that's as simple as this. So and you can keep doing this when you get home, and once you go through this it's very simple to understand how to insert tuple into the tree. Okay. And again, you can delete tuples in the tree, right? For example, what if you want to delete a tuple where age equals to 5 to the tree? So the algorithm is actually very simple. You find the right leaf node for L. You find the right leaf node L, and you try to remove the data in L. So there are 2 different scenarios. First one, if L is at least half full, then you are done. Okay. However, assuming L is too small, right? So you kind of need to merge 2 leaf nodes together, and then you delete the key in the parent, or you can borrow some tuple from the neighbors, and then you update the parent. Okay, so this is kind of very natural, right? So we will not go through the examples here. When you go back home, you can actually play with it, and there's the full specification of the algorithm is in the textbook. Okay, but intuition is very simple. So in practice, sorry. Sorry. So in practice, B+3 is a very powerful index. So here's actually some constant, right? So assuming, right? So you have a B+3 where your page size or node size is, for example, 8 kilobyte, which is somehow a little bit small in practice, but just for the sake of this example, assuming your kind of every single node in your B tree is like 8 kilobyte, assuming it can hold 200 keys, right? So the typical filling factor in B tree in practice is somehow like 60%, something like this. Which means that every single node will be like 67% full. Okay, so assuming that's the case, essentially the average fan out of the tree will be roughly like 130, right? So that's 200 times 0.67, right? So essentially for every single inner node, you are going to have, for example, on average, 130 children in this example. Okay, so given these constants, right? So let's see how powerful B+3 can become. So what is the capacity here? Essentially, if you have a B+3 with 4 layers, right? So that can hold like huge amount of entries, huge amount of tuples. So in this example, right, every single node has 130 children, right? If you give me 4 layers, right, so I can actually hold 300 million tuples like in this tree. So if you think about how large each layer is, right? So the number of pages per layer is, for the first layer, right, it's the root. You have 1 page, 8 kilobyte. And you have in the second level, you have 130 pages, which roughly like 1 megabyte, right? And in the third layer, you have maybe 17,000 pages, is like 140 megabytes. So when you have a tree with 4 layers, the first 3 layers, as you can see, is at most 140 megabytes, right? So in this example, all those 3 layers really, I mean, it's very easy to fit them into your DRAM, right? So essentially only your last layer, right? So the fourth layer is going to be in your hard drive, and the first 3 layers, highly likely they are going to be in your DRAM. So essentially, for every single time that I want to do one lookup in my B plus tree, I mean, I'm talking about one IO for that, right? So all the first 3 layers will be in my DRAM, right? So, and then I just need to bring in the right leaf node from the hard drive to my DRAM, then I'm done, right? So this is why B plus tree is so powerful, right? So like when you have hundreds of millions of tuples in your relation, right? With a very, very small buffer, you can have very efficient access. So now we talk about different access patterns, right? So like if you want to say, I want to do all the students where age equals to some constant, right? There are so many different ways you can do it. You can do sequential scan, right? You can do B plus tree, right? So what's the trade-off? Right? So when you are doing sequential scan over a heap file, you are going to have a lot of sequential access, right? So, however, in B plus tree, you are going to have a smaller amount of IO, right? Simply because I don't need to fetch all the tuples now. However, all those access will be random access, right? So as you can see, if you just count how many IOs you are going to have, clearly B plus tree is going to win, right? But on the other hand, all those access are random access, but for sequential scan, highly likely those are sequential access. So that is actually one very interesting trade-off. It's not often the case that the heap file is going to be slower compared with using B plus tree. Okay, so that's because sequential access can be faster than random access. That's true for disk. That's also true for memory at a different granularity. So there's a very dedicated trade-off between whether you want to do more reads, that's sequential, or you want to do less reads, but they are random. Okay, so in database there will be a cost model, and you fill in all those constants, right? So database will try to decide for you automatically which access method is the best one to use given what you want to achieve. So in reality, you can actually like there's a whole bunch of tricks you can automate both, right? So and database system need to take into consideration all of this to get a more realistic cost model. But as a user of the database system, you don't need to care about that. And that's the beauty of database system because it's really hide all those complexity from you as a user. So now let's get some intuition about relative trade-off, okay? So let's look at these two queries. So for Q1, I have a pond query. I want to find tuples in relation R with A equals to 5. In the second query, I'm having a range query. I want to find all the, so I want to find all the tuples in relation whose attribute is larger than 0 or smaller than a very large constant. Okay, so highly likely, right? So in many cases, maybe we should expect the database will actually use B plus tree for Q1. Why? Because we expect the number of result tuples is going to be small. Maybe we are not expecting too many tuples that are going to satisfy this condition. If that is true, right? So you actually do not need to do so many. What's this? You don't need to do so many like kind of random access. If you plug in that constant to your cost model, right? Highly likely you will have the case that B plus tree will be cheaper. However, if you are doing the second one, the Q2, if your expectation is most of the tuples in this relation will be returned, okay? If that's your expectation, then highly likely you're better off doing sequential scan, right? Because I need all those tuples anyway. I need to access all those pages anyway, right? So then doing one part of sequential scan is often faster, especially when you have an unclustered B plus tree, right? Because when you have unclustered B plus tree, and you end up returning a huge amount of tuples, you end up having a huge amount of random access, which is much slower compared with like the equal number of sequential access. Okay, so this is just one intuition about kind of the relative trade-off between B plus tree, both clustered, unclustered, and sequential scan. Okay, and again, the job of the database optimizer is really automatically pick the best one to use. As you can see, I need to estimate my expectation. I actually need to estimate in expectation how many tuples that each query is going to return. I mean, as you can see, that's kind of the key constant here, right? So next week, when we talk about database optimizer, we are going to talk about how database actually do it. So I think we have some questions. Go ahead.
What I wanted to ask is, for such a range query, would there be a way for the B plus tree to be better than a sequential scan, or if they are combined? Because I mean, if we can use the B tree to basically find all the keys, basically find all the slots where we would have to look for, and then we could tell, and then maybe the database would have a lookup table in which where then would just have to go through each and then kind of do a sequential scan. So wouldn't kind of.
Oh yeah. So for example, whenever you have a cluster B plus tree, that will probably be pretty good, right? So here, right? So you find the right leaf node and just scan it, right?
Yeah.
So
what I also was also interested in is, I mean, would it also just work to just, even if an unclustered B tree, you would still have the number of, you would still have the page ID and the slot ID, right? So you could just,
yes.
What you could just do is you could just go down, gather all the page IDs and slot IDs, and then just grab and then do one big scan over all the things while you with these elements, not in a random access, but just try to. Or is this too much?
I mean, so I can construct. Okay, so like for example, like if you do nothing in a naive implementation, what you do, you will fetch essentially all the tuples like in this page, right? So that could give you a lot of random access, right? But you could do something better. For example, I know I'm going to fetch the next 10 million tuples. Maybe I can do some better arrangement of my I/O such that I can batch as much of those I/O together as possible, right? So I could do that, right? So I could do that, right? So that's implementation specific, right? So you could have some implementation of the B plus tree that perform a little bit better than what we talked about in the course, right?
But it still will be beaten by sequential scans for the specific queries.
That's, I don't know, right? So that is to be honest, that's a database job to figure out, right? So so I can construct case where rearranging those I/O are not possible, right? So in those cases, maybe sequential scan is still better. I can construct a case where your trick can actually get almost perfect sequential access at the end. And then in that case, maybe you should use your implementation of the B plus tree, right? So like even with your trick, I can also construct different cases where one dominates the other. So the key that we want to get through is that it is database job, given your data, try to calculate some statistics and try to automatically decide for you which one to use. You have better implementation, then database have the corresponding cost model and still do the same decision-making process, right? So like whenever you have a new algorithm, like a new implementation, right? So the goal is the user will not make the decision on which one to use. The database will automatically do that for you, right? Yeah, I mean, you can keep optimizing each one of this. You can optimize the sequential scan, you can optimize B plus tree, right? So you can make both faster, right? So but the key is database is going to decide for you which one to use. That's the goal.
Thank you very much. You answered my question. Thank you.
Yeah, cool. Yeah, a very good question. Yeah, so B plus tree is something that you can do a whole bunch of crazy things about. If you want to optimize B plus tree, right? So there's actually a whole book about it. You can optimize the node size for different hardware, right? So and for different kind of workload, you can actually balance the tree in different ways. And some databases do some tricks, for example, they don't merge node with not half full, so on and so forth, right? So there's a, and also when you are dealing with integer key, they do one thing. When you have strings, right? You have all those perfect compression, right? There's a whole bunch of tricks you can do to make B plus tree faster. On the other hand, the whole bunch of things you can do to make sequential scan faster, right? So the goal is not really to argue which one is better for like over the other. We don't care, okay? We build a system to pick the best one for you, given your data. And that's what database try to do. So another thing about B plus tree that's kind of interesting is whenever you are building B plus tree over a relation, right? So there are different ways you can do it, right? So first approach could be slow, that you insert tuple one by one, right? So but you can do something slightly better. For example, you can actually first sort your data. Okay, we are going to talk about sorting on Friday. And then you just, for example, you have data like unsorted, you first sort it, right? And then you put them, like you kind of build a tree in a bottom up way, okay? So you put the, like, for example, like the height of the file together, 1, 3, you put this 3, you partition them to 3 different nodes, the tree kind of in a bottom up way, right? Whenever you are doing this, kind of like, for example, building a B tree index over a relation, often this is what happens under the cover. So in PostgreSQL, right, you can actually create the index over a relation, and then database will decide whether to use it or not, right? So the syntax is very simple. You just create the index, give it a name on a table using B tree if you want to use B tree, right? And you specify on which column you are going to do this B tree. So actually by default, using B tree is the default setting, right? So if you do create index name on table, highly likely there's a B tree and it's the cover. So on Friday, we are going to talk about something that can do slightly better on B tree on some workload, not all the workload, right? And that's called a hash table, right? So essentially the high level idea is whenever you are doing Pond query, B tree still have essentially the log mn complexity, right? Not complexity, but the IO overhead, right? So that's number of pages you need to read in the worst case. So can we do better, right? So it turns out we can, right? Given like if you want to do Pond query, right? We are going to talk more on Friday about hash table and other different ways that you can actually access data like on the hard drive. Okay, so that's all for today. I'll be here to answer a question you have. Otherwise, I'll see you guys on Friday. Thank you.
I've got a small question.
Yeah, go ahead.
Just maybe a misunderstanding from my side, but let's say we have a relation employee, and I think normally we can assume that we have multiple indices on a relation. So let's say one on age and one on employee ID. And that means only one of them could be clustered, the other one has to be unclustered.
Exactly. Maybe none of them is clustered, but you can have at most one cluster.
Okay, so that means that now if I do a query, as we've seen before, something like give me all employees from age 15 to age 100, which would be almost everyone, there is no way to do it sequentially, right, with the B trees. I mean, we have to do the random access if this one isn't unclustered.
No. So so there you could also choose to use the original heap file, right? So like you still have your tuple stored somewhere,
okay.
Right? So you can sequential scan that, right?
Yeah, sure, makes sense. Sorry, thanks for that.
Cool. Yeah, any questions? Okay, if there's other questions, I'll see you guys on Friday. Yeah.
I actually have a question.
Oh, go ahead.
Not sure if it's important enough. I don't see the problem with the. I don't understand the problem with two buffers. Like,
okay. Yeah, sorry, that part I didn't make that clear. It's my fault.
I wanted to know if it's really important to clarify, or is it just a brief explanation, and then we should just briefly know about it? Do I need
yeah, so I guess just, I mean, it won't be in the exam, right? So, but I still want you to know it, right? Okay. So I still want to explain that to you. Yeah.
Okay, so let me ask the question. Okay. in this case, we have 2 buffers. Is it correct?
Yeah.
All right. We have
Yes,
database
2 buffers. Yeah.
file buffer, and currently we have the blue thing in our DB buffer and red thing in file buffer. Now you say, hey, give me orange. DB says, give me orange, and then the disk. What the disk gonna do is take the orange and replace it with the blue one. Is it correct?
Oh, no. So essentially, when database say give me orange, right? So it need to try to evict the blue one to make space for the orange, right?
Yeah.
So when you try to evict the blue one, if you have update on blue one, right? So the file system is going to put that into the file buffer.
Why?
Oh yeah, because when you write something, the default behavior is you have the write buffer from the file system, right? So the file system will actually try to batch all the writes together and only minimize the I/O, right? So all the behavior is when you write something to the file, that won't be immediately flashed to disk.
Okay. Let me try to explain it again.
Yeah.
The scenario is we need the orange stuff from the disk. DB ask, give me the orange, and then because DB only have 1 slot, DB have to evict the blue. But after evicting the blue, the file buffer automatically grab the blue and take it to it. Is it correct?
Exactly. Yeah. So it's going to grab the blue, and at some point it's going to flash it to the disk.
Okay, I understand.
But but the default setting is not immediately, right? So I mean, you could optimize it, right? You could say, okay, I want you to flash the blue immediately to the hard drive, right? So then you won't have this problem, right? But that's not the default setting of the file system, right? And then also when you do that, there's also other problems because you have 2 buffers. Yeah.
Yep. All right. It's clear. Thank you very much and have a nice afternoon. Bye.
Bye. Okay, let's see you guys on Friday.